Welcome back. So if we recall the video from last time, you probably recognize these bases. We've just swapped the order. So alpha is now the standard basis and beta is now the basis 1, 1, 1, 2. I highly encourage you at this point to pause the video and see if you can solve these 4 questions on your own. And each day we're going to be doing these 4 questions as a part of the collection of questions that we do. And I encourage you to attempt them on your own, see if you can figure them out, and then come back and see if you are correct. You can always fast forward through the video to verify your answers. So let's get started. Here we want to know what t does to alpha. So this is 1, this is 2. What does t do to the standard first basis, or what is t of 1, 0? And this gives me 2 times 1 minus 0, 3 times 0 minus 2 times 1, which is going to be 2 minus 0, 0 minus 2, which equals 2 minus 2. Okay. We want to know what this is in terms of the vectors. 1, A1, 1 plus B1, 2. Well, now we're actually going to have to create a little bit more room. We're going to have to create a little bit more room because we can't quite fit all of our calculations. Because this is going to give us that 2 minus 2 is equal to A plus B, A plus 2B. We're going to have to solve a system of equations. And our system of equations is A plus B equals 2 and A plus 2B equals minus 2, which gives the following augmented system of equations. And now if we take R2 minus R1, replacing R2, we get 1, 1, 2, 0, 1, minus 4. And then R1 minus R2, replacing R1, gives us 1, 0, 6, 0, 1, minus 4, which gives us the equivalent system of equations. A equals 6 and B equals minus 4. Which means that we're going to get, we can store AB equaling to 6 minus 4. And that's the, you can see this as the coordinates of T10. Now we're going to look at what happens to our second standard basis. What happens to T2? This is T0, 1, which equals, and we're not going to do as many steps this time. We're just going to plug in 0, 1 into here, and we're going to get minus 1, 3. Now what we got to do is we got to determine what minus 1, 3 equals in terms of A1, 1 plus B1, 2. Well, we're looking at the same system of equations as, or this is equivalent to minus 1, 3 equaling A plus B, A plus 2B, which implies that we satisfy the system of equations A plus B equals -1, and A plus 2B equals 3. Okay. So this is how we're going to solve for A and B, and we create the augmented system of equations. 1, 1, 1, 2, -1, 3. Once again, R2 minus R1 replaces R2, giving us 1, 1, -1, 0, 1, 3. And now R1 minus R2 replacing R1 is going to give 1, 0, -4, 0, 1, 3. And we get the system of equations. A equals 4 and B equals, or A equals -4, sorry. Let's correct that. A equals -4 and B equals 3. So the vector AB can be stored as -4, 3. Pulling these together, we can create our matrix representation. T alpha beta is equal to 6 minus 4 minus 4. Now we have V alpha. So what is the vector 1, 3 in the standard basis? Alpha. That's our question. And to answer it, we look at 1, 3, and we want to make it using a linear combination, A of the first standard basis plus B with the second standard basis. It's going to be 1, 1, 0 plus 3, 0, 1. So my coordinates are going to be 1, 3. So this equals the vector 1, 3. Now we're asked to compute what T of V is. And it's the same computation we did in the last video. We have 2 times 1 plus 3 times. Oh, let's make sure I got the right expression. 2 times 1 minus 3, that's right. So 2 times 1 minus 3. And then we have 3 times 3 minus 2 times 1. So 3 times 3 minus 2 times 1, which equals -1, 7. So now what we're going to do is we're going to verify that the representation of T of V in beta, we want to show that this is also equal to T represented using alpha beta, or the matrix representation of T using alpha beta times the coordinates vector of V and alpha. We want to verify that these are equal. So first we're going to look at what is the representation of -1, 7, or the coordinates of -1, 7 in basis beta. To answer this, we want to look at -1, 7 equals A1, 1 plus B1, 2. And this creates a system of equations, which I encourage you to work through. How can I get the system of equations? But the system of equations we're eventually going to get is A plus B equals -1 and A plus 2B equals 7, which gives the augmented matrix 1, 1, 1, 2, -1, 7. We take R2 minus R1, replacing R2. We get 1, 1, -1, 0, 1, 8. And then R1 minus R2 replacing R1 will give 1, 0, minus 9, 0, 1, 0, or 0, 1, 8, sorry, which gives the following system of equations. A equals minus 9 and B equals 8. So this means that our coordinates vector is going to be minus 9. Now we want to verify that this is what this multiplication is equal to. So let's get our matrix multiplication, which is 6 minus 4 minus 4, 3. So 6 minus 4 minus 4, 3. We're going to multiply it by 1, 3. And we get 6 minus 12 and minus 4 plus 9. So there's something that I have done wrong somewhere. Let's take a look and see if there's some subtraction that we do. 4, 6, oh, that's right, 6 minus 1. And now, oh, here it is. This is supposed to be a 4. So this becomes a 4, and this becomes a 5. Oh, let's erase these. So this becomes a 4. This becomes a minus 5. 4. This is minus 5. 4. This is a minus 5. 4. So our matrix becomes minus 5, 4. And now here we get minus 5, 4. And now minus 5 times 4 is 15. And 4 times 3 is 12. And when we subtract these, we get minus 9, 8. We can see that our two vectors do in fact match. And we're, after a little bit of error checking, happy with it.